Hello, everybody. So, welcome to the AI/ML cohort, May 2026 at S30. Just a roadmap of the logistics or the things that we will be doing in our cohort. Firstly, the books that we'll be following is for the mathematics part. We will be following the Faisal and Desnoth book. This one book, Mathematics for Machine Learning, uh, as our curriculum book. All right. So I will be referring to this uh, book a lot in the class as well. And the second one is the very famous machine learning book that is O'Reilly Geron. This is this book. If you're looking for to buy it, then the deep learning part we will be going to Goodfellow. That is this book. All right. I'll send you the links also. And for the system design, we'll be following the O'Reilly book also for which is designing the data interview applications by Clapman. All right. So these are the books as far as books are concerned that we will be that I will be referring to if we are going a little bit of you know very under the hood things, but as far as classes are concerned, we will be fine with our labs. That is, we have the labs at ai.theaesthetic.com. We'll be focusing on these labs. These labs are structured into different ways. So for every lab, we'll be having a theory portion, which will be right here, which we'll be covering before we start coding, but theory portion. And then we'll be going to the exercises. The exercises we have, it's just like a lead code for AI/ML, where we'll be going to an exercise. We can reset it, whatever. If there is a solution, we can have the solution right here, and we can run it, and it will give us the outputs or the errors that we'll be getting. All right. So most of the time that will be spent in the class will be on these labs that we'll be doing. So firstly, the theory part, and we'll be having discussion about it, and then we'll be doing the task actually, and we'll be all the models, all the advanced models will be built into these labs only. And another thing, there is another part to it, that is, if you want to have subsequent notes that I have done myself, I have built myself when I was learning about these things, is Substack notes, which are right here. So on top of this, every lab, you'll be having Substack notes, which you will be able to see what we are covering in the classes more or less is covered in the notes as well. I keep posting a little bit of the snippets of learnings on YouTube also on my channel. So if you want to follow that, then you can follow that also. Not necessary though. We will be covering most of the things in the class only. All right. Anybody, any questions about the logistics? Anybody who has not signed up on ai.theaesthetic.com, please do sign up and do let me know. Because if you are enrolled in an AI/ML cohort, then there is a complimentary membership of 1 year, which is already given to you on the labs. It's not a free platform; it is a paid platform. But if you are enrolled, then it is a free platform for you for 1 year. All right. So when you sign up, then please do let me know so that I make your account as premium. All right. Anybody, any questions about the logistics? Yeah, I can send the links to the books later on. All right. So let's get our feet a little bit wet today. So we will be learning about machine learning. What is machine learning? We are getting into the classical machine learning initially. What is machine learning? What do you understand by it? Or what kind of machine learnings that you have come across? Are you guys
Linear regression, logistic regression, like it's basically prediction. First,
basically prediction? Okay, prediction.
we train the machines to predict. First, we train it on the known data, and then we can predict based on the
Okay,
unknowns.
that's a good start. Anybody else? So we have two different kind of machine learnings: supervised machine learning and unsupervised. Okay, that is a classical machine learning that we are talking about: supervised and unsupervised machine learning. But before we're getting into the types of machine learning, let's understand what is machine learning. Machine learning is basically extracting the valuable information from the data. All right. It may be in the form of the prediction. Absolutely. But machine learning is, we have to go to the exact definition, is about designing the algorithms that automatically extract valuable information from the data. All right. So that is machine learning. There are two kinds of machine learning: supervised and unsupervised. What is supervised machine learning? What is the difference between them? You can use any of the resources. You can use ChatGPT. In fact, I encourage you to use ChatGPT when you are doing the labs by yourself. Also in the labs, you will get an option of talking to the ChatGPT as well. All right. So you can very well do that. All right. So supervised machine learning is what? Anybody?
If we have a
The
target,
datas are labeled.
Labeled data. When we have a labeled data. When we have non-labeled data. What are some examples of supervised machine learning model?
So supervised is more like, we give the input and output and say the
Yes.
model, make it happen. But in case of unsupervised, we just give the input and the data set is unlabeled and say it like, go figure it out with the
Yep.
patterns.
That's a great way of putting it. All right. We have non-labeled data. Here we have labeled data. What are some examples of the models which are labeled data?
Classification.
Classification. In classification, what are the different models, specific models?
Logistic,
logistic
linear,
Logistic regression,
linear,
decision trees, random
decision,
forest,
random forest. Perfect. What else?
X,
Anybody else?
XGBoost, SVM.
XGBoost, SVM. What is some examples of not unsupervised machine learning?
Clustering.
Clustering.
K-means,
K-means clustering. Okay. What else?
PCA.
PCA.
Yeah.
Mhm.
ICA.
ICA. PCA stands for
principal component analysis.
principal component analysis. Okay. All right. So nil we understand that, okay, in one we have the label data, in one we have the non-label data. And when it comes to another way of mental model of machine learning is that we will be having three things that whenever we are going about a machine learning model, we will be having data. All right. We will be having the actual model. And we will be having learnings, or we can call it matrix. What are the matrix? Or so we'll be dividing our brain into three things. We will be focusing on three silos. One is data, one is model, and one is learning of the matrix. All right. Then comes the next part. What we are going to learn today, or we are going to understand, is NumPy. What's NumPy?
Library for making mathematical operations.
Mathematical operations. Okay. Mathematical operations. Anybody else? Okay, let me ask a leading question. Where does the NumPy fit in these three things?
Data.
And for analyzing the data.
Data. Anybody else?
Matrix.
Huh?
Like
Matrix and vectors.
Metrics. Okay. Anything else?
Vectors.
Models. Does it fit in model?
No.
So actually, NumPy fits in all these three things. In fact, all the models that we'll be writing, all the models which are written in any of the libraries. They are written on top of NumPy. So NumPy is the basic engine. Whether it comes to cleaning of the data or extracting the data, we will be using the libraries like Pandas, which is built on top of NumPy. We will be writing the models. All the linear algebra which we will be doing is based on NumPy. And all the matrix that we'll be having will also be built on top of NumPy. So everything which we are going to do in machine learning is built on top of NumPy, and we'll be using the NumPy as the base engine. It is the engine for all these three bogies of the train. All right. So NumPy is the engine. It has to do the data, model, as well as the matrix. What's so special about NumPy and why we need a library? We have Python, right? The whole of the machine learning is, I thought it was Python. Everybody told me it was Python. Then why I cannot use a normal Python? Why I have to use a library like NumPy? What's so
Python is
Python
special?
slow.
is really slow, and NumPy is under the hood. It's written with C++, which is fast. And for the numerical computations, it's much better to use this library than using in Python.
All right. So NumPy is written under the hood in, actually, it's not C++, it's actually C. All right.
Compile C.
All right. So NumPy is super fast than the normal Python. So first and foremost thing that we have to keep out of the machine learning is our Python mind. We have to get into the NumPy mindset. NumPy mindset is NumPy under the hood is compiled C code. Why is it fast? Because it's compiled C code. It doesn't have, if I have to write 4 things about NumPy, then it is compiled C code plus. Why is it fast? Is SIMD. The next thing that we have to talk about is no interpreter, because it's compiled already, right? Like Python. The fourth thing is cache. All right. So CPU caches, compiled native code, no interpreter, SIMD. Compiled C code, we understand that it is basically we have lists. All right. What is the advantage of a compiled or a list or an array of C over a Python list? What is first part? What is the advantage of C kind of array or a data structure rather than Python?
Contiguous.
Contiguous memory.
Perfect. It is contiguous memory.
And it occupies less bytes. Since Python, we have the objects
Okay,
in each.
good.
Yeah.
We'll talk about that. Contiguous memory. What else?
Cache friendly.
We'll talk about cache when we go to the cache. Yes, it is related to cache.
Maybe like pointers, like you have direct reference to the memory, which
Remember,
is not.
contiguous memory and same data type. All right? Having the same data type helps. Why? Because if you have Python, if we have multiple data types, then we need to use the interpreter. To compile the code first, we have to use the interpreter, because it may be possible that right here I have one, and right here I have blah, a string blah. So a non-contiguous memory at blah. Here I have just the integers only. A contiguous memory, which doesn't need any interpreter. It is compiled. All right. So it is super fast in nature. What is SIMD? Anybody? All right. Our CPUs are, or any computing, all right? Data, model, learning and matrix, engine is NumPy, which helps us in compute. compute is required for data, for modelology, for learning and matrix. Every unit, for example, CPU or GPU, every unit has MIMDs. That is multiple instruction, multiple data. For example, Omkar's favorite singer is Taylor Swift. He wants to comment on her latest song. And then he has opened up the terminal and he is trying to run a model. He is doing multiple instructions to his unit. And in the multiple instructions, multiple data, for the single instruction, we have SIMD. That is single instruction, multiple data. That is in the case of CPU. All right. Super fast. On multiple data, we can do the parallel operations. We'll see it. Don't worry. We'll go under the hood. And in case of GPUs, we have something called SIMT. What will it be? SIMT?
Single instruction.
Single instruction?
Multiple tasks.
Threads.
Process. Right.
Multiple threads. Now we are talking about threads. So if there are multiple threads which are running on the single, with the single instruction, then it's super fast. Let's see it in action a little bit. If we have a list, if we have an array, 1, 2, 3, 4, and we have another array or a list, and we want from this 5 plus 2 plus 6, 3 plus 7, 4 plus 8, and the result should be like 6, 8, 10, and 12. That should be the result. In order to go from here to here, what should I do? In a normal language, what should I do? Or in Python, what will I do?
For loop.
I'll do a for loop. I'll do an iterator. I'll do a for loop. All right. Ith index 0, add both. Get this, get this, get this, so on and so forth. All right. But in NumPy, we have vectorized operations. Vectorized operations is nothing but compiled C code plus SIMD plus no interpreter plus cache. In that, what happens? In the single instruction multiple data, what happens? All these four are just directly, think of it like a waterfall which falls onto this and does the plus operation. So rather than doing these four separately, in single instruction, all these are added. And we do not need to do this. Looks very rosy. But how many operations in parallel we can do? Can't I do 100? Can't I do 200? Who decides how many operations in parallel we can do? Single instruction, multiple. What's the multiple part? How much multiple? Who decides that?
CPU.
CPU. CPU decides. And for example, Lohit, which system you are using? Which machine you are using right now?
Mac.
Mac Pro.
Yeah.
What is the SIMD capability of your RAM? Of yours, not RAM. SIMD capability of your CPU? You might not have seen it, but it is 128 bit. All right. My integer is a signed integer. If it is a signed integer, how much space it is going to take? How many bits it take? What is the memory of an integer? 4 bytes, huh? 4 bytes. How much is 4 bytes? 32 bits.
Right.
How many 32-bit integers can be there in 128? 4. That's why I was taking 4 as an example. So I will be having 4 operations in parallel. That is the SIMD part. Another thing is that I have just the integers, contiguous memory. I do not need an interpreter. Since we have the compiled C code, then comes the caching part. Your memory in your unit is RAM. But apart from RAM, you have some caches, temporary cache. What are those cache names? Those are called, firstly, the main memory RAM, then L3 cache, then L2 cache, then L1 cache. Some instructions and some data can stay in L1 cache if it is compiled. And that's where the power of C comes into the picture. The instructions and the data, the system can keep it at the L1 cache level and extract it very, very fast. These 4 things combined give us vectorized operations. I am still not convinced. Okay, these are doing vectorized operations. We'll talk about what is vectors. Just a moment. But how much you think will be the effect of these vectorized operations on our speed? I think machine learning people have been crazy. They should have gone for Python only. But if at all they are going with this, how much will be the effect of the vectorized operations? Any idea? Anybody knows the benchmark? Let's look at the benchmark. We are going to do an exercise tomorrow, which is going to look at the loop versus vectorized operations. All right, in which we will be having just a single standard normal array of 1 million elements. Not a very big data, very small data. And we'll be running a for loop on it, in which we will be subtracting the mean and we will be dividing it by sigma. Basically, we will be standardizing the data. All right. So if we have to run that, I'll take the start time and I'll take the loop time. That is the end time of the for loop. And the other one is the vectorized operations, in which we are just doing the vectorized operations. We come to that. How do we do the vectorized operation? But just to give you an idea of how much is the difference is about 100x. Just for this exercise, in which we have a list of 1 million elements. All right. So we are talking about a significant increase in the speed rather than the Python for a simple operation like just iterating over an array of 1 million elements. Does it make sense? Anybody, any questions till now? All right. I've been throwing around this word a lot. Vectors. Vectorization. Vectorization is basically which is happening these things under the hood. But what is vector?
It's a matrix.
If it is a matrix, then what is it?
Embedding data in a particular form.
Embedding data in a particular.
Convert the data into a number so that we can plot it in a multidimensional graph and analyze the patterns.
Too high level. Okay.
So matrix is 2D and vector is more than that, like 3D.
Just. So let me answer him, Shravan, first. Okay. So what you are defining is using under the hood the vectors. All right. That is one use case of vectors, but under the hood, everything is going to be vectorized. Everything is going to be a vector. We have to start from the basic unit. All right. So yes, the graphs maybe will be using vectors. All right, but that's not how we will be starting. All right, and somebody was okay. There was a female student who was saying, please go ahead.
Embedding
Yeah,
data
so
in particular.
Embedding data. All right, no, not really. If I okay, just if I don't have to embed the data, if I don't have to embed the data, does it mean that the vector will not be there? That there is no use case of vector? Okay, yeah, yes, Pooja, go ahead.
matrix is 2D and vector is a plane. Like if I have to represent the data in a plane like 3D.
Okay.
Yeah. So matrix
No.
is a subset of vector.
Okay, the 3D one is called a tensor actually. All right?
Yeah.
2D is called a matrix, 3D is called a tensor, 1D is called a vector. All right?
Like
It has
multiple values
direct,
which we want to process together. We can say that.
Yeah, okay, we'll see.
it has direction and length in
Okay,
terms
good.
of physics.
That's good. Okay. So there are three views of the vectors. All right. There are three views, and once in the machine learning, once we go into the deeper machine learning, then there will be a lot of random switches between these definitions. So understand the distinction right now only so that you don't get confused. There are three views of the vectors. One is a physics student view. Physics student defines the vectors, and we will be using all these three views in machine learning. All these three views are going to come into the picture at different times of the explanation of the things. And you will be thinking, oh, he was saying the vector was this only. No, he's talking about this. So you have to switch between your hats. The physics student hat says that a vector is the one which has magnitude, or we call it sometimes norm. Just throwing out some of the terminology. Norm or magnitude, it has magnitude and it has direction. Very important when we will be coming to the embeddings, LLMs, same direction words. Going, gone, went, gone. We'll be having the cosine similarity based on the directions. All right. So one is the physics student hat, that is magnitude plus direction. Another one is computer science student. All right. Another one is computer science student hat. According to that definition, is nothing but a list of numbers. Just numbers. Whether it is strings, whether it is any embeddings, anything. Everything is going to be condensed or converted into a list of numbers. That is a computer science hat. We'll not be talking about direction at that time. We'll not be talking about the magnitude at that time. And the third hat that we'll be having is a mathematics student. Hat. According to a mathematics person, vector is nothing but which has two properties. What are those properties? Can be multiplied by a scalar. One property. Another property is that they can be two vectors can be added together. All right. And I'll tell you the distinction. For example, in whiteboard, I will be saying the mathematics student says that the two vectors can be added. This is one vector. This is another vector A, B, magnitude and direction. So mathematics students says that they can be added, and this will be the resultant vector. C. So for representing on the whiteboard, I am taking a physics student view of representing the vector. For addition, I am taking a mathematics student view that they can be added together. For implementing it, I will be taking a computer science student. NumPy comes right here, compute. Make sense? So on the whiteboard, we will be representing the vectors using physics students hat. The operations that we will be doing is mathematics students hat. The implementation or the engine will be computer science. So you have to be a physicist also, you have to mathematician also, you have to be computer science student. That is the way that we will be doing the vectors. For a computer science student, vectorized operations are on a list of numbers, which is having compiled C code, SIMD, caching, no interpreter. Because we are just worried about the computer sciencey part of it. Doesn't mean that we will not be taking the physics view of the vector or the mathematics view of the vector. It's just the implementation layer that we are talking about. Anybody, any questions till now? Let's go further, because I do not want to disappoint him, Shravan. He said, or I do not want to disappoint Pooja also. Every data structure or every data structure that you will be presenting for a computer science student will be in the form of the list of numbers or vectors. How? For example, very famous in machine learning, Heinz Shravan is developing a recommendation system. A recommendation system, should I be giving a loan to this guy or not? His salary, his age, his address, or number of years of experience. Are in the form of a table. He's doing a recommendation, loan, no loan. For him, that can be the target. Or a 01010. He has a salary, he has age, he has number of years experience. These are called samples. ID 1 or name, Omkar, who is looking at WhatsApp right now, is first sample. Then Nitish, who is the next sample? His has salary, age, years of experience. Make sense? And then Bharat is next sample, so on and so forth. These are called sample in your data. These are called features. All right? Features. Salary is a feature, age is a feature, years of experience. You can call it columns also. We call it features because tomorrow there is feature engineering going. Not tomorrow. Some days after, we will be talking about feature engineering also. The features are vectors. This data is in the form of a matrix. But all these are vectors. 1D vectors. Vectorized. Always stay in the mindset of vectorized. Make sense? So we can carry out vectorized operations. At the runtime, even the samples of Akshay right here, they are also converted into vectors. So if you have to do the operations this way, you can use the vectorized operation. You can use the vectorized operation, you have to do the things this way. In machine learning, we will be calling this, if we are doing the operations like this, it's called axis 0. On the axis 0. Remember that. If we are doing the operations like this, then we will be doing axis 1. So in NumPy, if we specify the axis 1, then I'm doing the operation like this. Let me take a physics student hat. If my vector is this, a sample, then these are the, if I am just representing based on age and salary, then I'll be representing, oh, this is the Akshay vector. Basically a point in the, that this is his age, this is his salary. If the third feature comes in, which is protruding out of this whiteboard, then that will be the years of experience. Make sense? So that's why vectors are a very important thing, because at the computational time, we will be doing only the vectorized operations. But doesn't mean that that is the only vector, that it is a list of numbers. You can take a physics student hat, also you can take a mathematics student. Or the linear algebra, or the probabilities, or any mathematics operations that we'll be doing, mathematics that we'll be learning with a hat of mathematics student, but implementation will be done using computer science student's hat, which is NumPy hat. Anybody, any questions till now? All right. Now, yes, Lois, go ahead.
Yeah. So I'm just like trying to clarify here. So like just based on the representation table that we have. So if we are doing a column scan, so essentially we are saying that okay, axis 0 is a representation for it. But the operation that we do, is it on the vector or is it on the NumPy? Like that's what I'm confused with.
This age is nothing but a vector, which is basically a NumPy array. Make
Okay.
sense? Remember,
Okay, got it.
a vector for a computer science student is just a list of numbers. A NumPy array. Make sense? A
Got
NumPy
it.
array, why? Because we can do the vectorized operations on it.
Okay.
All
Got
right. All right. Anybody else? Any other questions? All right. Now let's go to some of the common things that we will be using in NumPy. Although we are just, we are just having a little bit of introduction to NumPy only. There will be some other operations also which will be coming, but all those operations will be NumPy operations, will be vectorized operations. Today we are just looking at some of the operations that we are doing. Okay, one more thing, which is very important. NumPy distinguishes between vectors and matrices. Although matrix is nothing but a collection of vectors only, it needs a distinction between the vectors and the matrix. And the way that we do is with the shape. We know what is the shape of the data structure. NumPy array's shape, if we have a 1D array like this, 1, 2, 3, 4, and if I call on this NumPy array X, if I call dot shape, what will it give me?
4, comma.
4, comma. That's it. All right. This is the NumPy array. This is NumPy telling me that this is a vector of shape 4, nothing. 1D array. Is this same as 4, 1? If for a data structure, if I take the shape, because for our normal data structures, we don't distinguish. We say that 1D array is matrix of row 1, row length 1. But in NumPy, these two are totally different things. 4, comma, a 1D array is a vector of 4 elements. And 4, 1 is a matrix of 4 elements.
Oh.
Two different things. And we'll see, we'll represent them, that how they are represented. All right. Shape is basically telling us the dimensions of the data structure. Just a little bit more on that. Let me see if I have. Okay. Okay. So in the real world, shape 3, 1 3 rows, 1 column is a matrix of 3 rows, 1 column. And actually, it will be looking at first row, only 1, second row, 2 only, third row, 3 only. And I will be having the matrix like this in case of NumPy. It's totally different from 1, 2, 3. So this is a matrix. See the nesting. 1 outside brackets, then inside brackets. Over here, just the outside brackets. This is a vector. This is a matrix of 3, 1. 2 different things. And just to 1, 3. 1 row, 3 columns. A matrix of 1 row, 3 columns will be represented like this. 1 row, 3 columns. Make sense? See the nesting. This is different from this. Yeah, but can anybody know why is this distinction required? People don't even come to know that this is different. But why is that distinction required?
To do the proper addition, multiplication.
Okay.
All those operations.
Can't I do it with only the vector and the one? What's the difference between 3, 1 and 1? 3 only. You're right. So vector operations and matrix operations are going to be different. We'll see. The vector multiplications and the matrix multiplications are going to be different. And it circles back to the same concept of mathematics student view. What are the operations that we can do? Just the scalar multiplication. And the second one is, this is the wrong finger for that. The second rule is the one that we can multiply it with a scalar and the 2 vectors can be added. All right. And we will withdraw the matrix multiplication from those 2 operations. Matrix operations and vector operations are going to be distinct. There is a difference in that. That's why the NumPy requires a distinction between them. The second thing is broadcasting. Broadcasting is a concept that we'll be learning, which is an amazing concept as far as computer science student. You will fall in love with it. It saves so much of time. It saves so much of memory. Broadcasting of the vectors and the matrices are going to be different. Hence, we need the distinction between, and broadcasting is used a lot. All right, let me tell you, any machine learning engineer who has done even a few lines of code has been using the vectorized operations and the broadcasting. All right, so now let's go to once we have understood these things, these basics, now let's go into the lab a little bit. We are importing the NumPy, we are importing the time, because in the later on stage, we have to work with the time and see how much loop takes, how much vectorized operation takes. And a standard check function, which is basically for doing the tests under the hood. The tests are already written. All right, I'm going to reset it. So first exercise is that we have, okay, let's go with the theory a little bit more. All right. We have already talked about the C and the contiguous memory typed vectorized operations. Let's talk about the creation and the shapes. All right. So if we have to create an 1D array of 3 elements, then we can create it like this, directly like this. All right. All right, let me write print a.shape. What will be the shape? What do you think?
Nothing.
Why?
Empty.
3.
It's a
3 comma.
vector, right?
Yeah, 3.
3 commas.
Yeah, 3 comma, that will be the shape of A. All right. If I want to have a 2D, then I can have comma, the next row, 4, 5, 6, and then nested it. So 2 rows in the matrix. So 3, 2. 2, 3, sorry. 2 rows, 3 columns. That will be the matrix, and I can initiate the matrix like this. But I don't want to write, I'll be having so much of data, I don't want to go 1, 2, 3. All right. So if I want to write a numbers from 0 to 99, then we can use something called a range. np.arange up to 100 will give me print of array 1D, will be giving me numbers from 0 to 9. And we are using the function that is arange, 0 to 99. So the 100 will not be included, it's excluded. We can have 0 to 99 with arange function. All right, let's look at few more things. That is, if I want to create a np, an array A of np.zeros, and just one dimension. If I create one dimension only, then print A, what will it give me? A vector of
5 zeros.
5 zeros. How do I know it is a vector? I just write the shape. All right. If I give it two dimensions, if I give it 5 by 5, see, if I'm running the cell, it gives me an error. Cannot interpret 5 as a data type. Why? Because it cannot interpret. If I have to give the two dimensions, I have to give it in a form of a tuple. All right. So just play around with it. Now, if you do it, you will be having a 5 by 5 matrix of all the zeros. All right. Oops. Where I was. Ooh. What happened? Yeah, print A. All right. A 5 by 5 of zeros. That's why it is a tuple. Cool. And remember it. Because for 1D, I will be just doing one single bracket. For 2D, a tuple. For 3D, also a nested. Huh? If I have 5 by 5 by 5, a matrix of 5 zeros. 5 zeros, 5 depth. 1, 2, 3, 4, 5. Cool. All right. So if I want to have ones, I can have ones also. A 2 by 3 matrix of ones. 2 rows, 3 columns. What is the data type over here? Float, huh? Remember it. That what is the default data type? We'll talk about how we can change the data types also. And then what is I, np.I? An identity matrix of 3 elements. Sorry, an identity matrix of 3. Basically, it gives me a 3 by 3 matrix with all the diagonal elements as ones. It's called identity matrix. 3 by 3 matrix, it is a matrix. If I do shape, 3 by 3 matrix. These are some of the common things. And A range, if I have between 0 to 10, 2, then basically it will be giving us the numbers from 0 to 10, but at space at an interval of 2. So this is interval. 0 to 10 range, and 2 is the interval. Cool. And we'll be using, in fact, the linear spacing. This is called np.linear space. Between 0 to 1, a linear space, 5 spaced at 5 intervals. So 0, 0.25, 0.5, 0.75, 0.1, 1 point. All right. That's how we'll be doing the linear spacing. And then if I want to have a standard normal, then I can use np.random normal. And I will be having a random normal of 3 by 4 matrix. 3 rows, 4 columns, and random normal data. We'll talk more about random and random normal later. Now let's come to the A range only and the reshapings. Very important. Give me full concentration now. np.A range of 100 element will give me print. Array 1D will be giving me 99 elements. Now we have to reshape this array 1D into 10 by 10 array. And for that, I can do array 1D is I have to do 10 by 10. Remember tuple. All right. If I print array 2D now, what happened? line 12. Array 1D dot reshape. All right. So now we have a 2D array. Cool. Now, if we want to create a 3D matrix of 4 by 5 by 3 shape, then all I have to do is for 4 by 5 by 3 shape, how many total elements can be there?
60.
Perfect. Chanika is absolutely correct. So NP dot A range of 60 elements, 0 to 59, and reshape it to a 2 pala 4 5 3 4 5 3. If I run it, it passes all the test cases. Don't worry. Basically, in the test cases, we are checking the shapes. First one is 100. The second one is 10 by 10. The third one is 4 by 3, 5 by 3. And one more thing, shares memory. Everybody will tell you that, okay, how to reshape. But what doesn't everybody tell us is this, that if I do array of 2D, 0, 0, 0, 1, first row, first column, first row, second column, I am making it 999. All right, 4 nines. If I print it, this element is 9999. But surprise, surprise. Give me full concentration now. Print array 1D now. And that array 1D also will be having 99999. What is the conclusion? Array 1D and array 2D are sharing the memory. And that's what we checked over here. It means reshape just does one thing, it creates a view. It creates a view. So see how much optimal it is. It is not creating a deep copy at all. So Omkar has created initially a 1D array of 1 million elements or 10 elements. I cannot have 1 million on the whiteboard. You will hate me for that. If I have 1, 2, 3, 4, 5, 6, 7, 8, a 1D array of 8 elements. And then I reshaped it. It is at Mr. 420. I reshaped it. I have a 2D array, which is on your code, in your code, when you're printing it, looks like, if I converted it to 4 by 2, 8 elements, then you are looking at it like this, that it is 1, 2, 3, 4, 5, 6, 7, 8. All right? Or 2, 4. All right? 2 rows of 4 columns. 2 rows, 1, 2, 4 columns. Looks like this. But nothing has changed. This is given from 420 itself. And the way NumPy does it is using strides. It creates a stride right here, first row and the second row. Strides. NumPy under the hood creates the strides. Right here, one stride. Right here, one stride. If you print the strides over here, it will be giving you a number like 16 and 4. Basically, it creates a view only. It doesn't create a new shape. It creates a strides or just markers. 16, 4. It means the first row, every row, not first row, every row is 16 bytes. 4 plus 4 plus 4 plus 4. That is 16. And each column, each element, 4 bytes. Integer, no. This is what is going on under the hood. So if you reshape it, reshape doesn't create a new deep copy like that. It is still at 420 only, but reshape has just reshaped this data it has not created anything new. It has just created strides. It has just, in the metadata, it has created 16-4. So if I go right here, if I look at array2d dot strides and array1d dot strides, we already know this is containing the metadata of the reshape. If I print it, if I see the strides of my 2D arrays 40 to 44. Why? Because 10 into 4, 40. And each column 4 bytes. And the first one is 4 bytes on. So reshape just creates a view on it. It doesn't create a deep copy. It is still the original vector on. The revolution has happened. You didn't realize it. This is how the vectorized operations will be taking place. Even if you have 3D matrix, 4D matrix, 5D matrix, 30 dimensions. Under the hood, it is 1D, on which I have strides. Make sense? See how simplified it is under the hood. All that data that you are thinking in 30 dimensions is actually a 1D data. Anybody, any question till now? Is your mind blown or not? Not yet. Don't worry. We'll blow it. All right. The next part comes that we want to work with the data types, right? I have the different data types. So we want to create, in the next example, reshape doesn't copy the data, it creates a view. Very important. Indexing and slicing, we will be going to indexing and slicing, but firstly, let's talk about the data types and the memory. If we have an array of integers, we want to create an array of integers. Let's create a base array of np.range, a range of 1,000 elements. I can write the 1,000 like this. This is more readable in case of NumPy. Okay. If I print base, okay, then I will be having, what's the issue? Oh, dot, dot, dot. Something
I think you
else.
added underscore between 1 and 0.
No, that is should not be the issue. Something else is the issue. Okay, it is not. Okay, ellipsis. But it should have printed. Yep. Okay. The ellipsis was the issue. Okay, if I have 1,000 elements, then I'll be having a 1D vector of 1,000 elements. And I can write it like this also. Okay. This is more readable. Okay, 1,000 elements. But what's the data type? If I print base.d type, is going to give us the data type. So data type is going to be int32. So if you are initiating a range vector, then it is initiating with int32. I can very well specify d type to be two ways, that int64 or float. If I represent the float, then the data type will be float right here. And the base array will look like this. Floats. 0.1. Float. All right, I can represent the data type like this also. I can represent the data type like this also. Please don't hate me for this. np.float. All right. So, np. I forgot.
It's float 64.
Float 64. Yeah, you are right. Okay. Float 64. All right. I can write it like this also. All right. So this is the way that I can specify the data type. Or I can do this also. That we want to have an int array of int. All right. I don't know what it is initiated with. If I want to, base.asType. AsType. Int 30. All right. And base.asType of float 64. All right. So now if I print array int, and print array float, then you'll see the difference between them, that one has different data type, another one has different data type. This one has, I just want to have only 5 elements from this, 0, 2. And I want to have just 5 elements from here also. We just did a little bit of indexing. All right. So there is a difference. All right. You can look at the data types also. D type and D type will be different. All right. One will be int 32, another one will be float 64. All right. And no, needless to say that I can do this also. np dot int 32 as well. All right. Same thing. Samira. All right. This is the data types. And then we'll be going to the index views and copies. All right. And especially we have to be worried about the normal indexing and the fancy indexing. Firstly, we are going to create a 1D array of, create a 2D array and slice every alternate row. Okay, let me see how much is the length that I should be creating. Okay. I am going to create a first array of 20 elements. All right. So np.a range of 20, and I'm reshaping it to 10 2. If I have to create a slice in which we have to just give out, for example, let me print A. If your use case is that out of this 0, 1, 2, 3, remember 10 by 2 matrix, huh? If we have to create like this, we could have created the matrix like the other way also. It's just I'm using the array range. Or if I want to create a slice in which I just want to have this row, then skip the next one, then have the next one, so on and so forth. I just want to skip. Then I can do this. A, print A slice. Mind you, these are going to take different memories. Why? Because one is 4 bytes, another one is 8 bytes. So they cannot be same view. They have to be deep copies. All right. Reshape is not. You'll see the slice is also not. It's just a slice on the view itself. It doesn't create a new deep copy. Just like Python, for all the rows, for all the columns, have a spacing of 2. That is, if I do this, then 0, 1, 4, 5, 8, 9, 2, 3, 16, 17. So we are eating out 2, 3, and then 4, 5, then 6, 7 is eaten out, 8, 9, so on and so forth. Interval. No? All right. And if I modify a slice and observe A, then both are going to take the same space. Why? Because I changed A slice to minus 999, the A also changed. This is basic indexing. I can represent it like this also. A comma. All right. Let's look at a few more indexings. All right. If we have an array like this, few more indexing. This is the indexing. This is called basic indexing. If I want to have from this array the very first element, so print array, very first element, then I can do it like this. Sorry, I want to print 20, then I can print 20 like this also. I can print 20 like this also. Everybody will tell you that you can do both, but both have different significance. This is basic indexing. And you will realize that this is fancy indexing or chained indexing. You can get the 20 like this, works. But Remember, we are doing it like this. And you realize that chained indexing is no. Basic indexing, which is right here, is yes. Why? Because we will realize later on in this exercise that fancy indexing, which is basically the chained indexing, does create the deep copy under the hood. All right. So get out of the word of the DSAs and get into the word of NumPy. This will be the basic indexing if I want to get 20. If I want to get for all the rows, I want to get 50, 60, and 80, 90. 50, 60, and 80, 90. What should I do? I need to get 2 rows first, okay? So if I want to get 2 rows, 0 to 3, 0 to 2 if I do, so 1 to 2. Then it will be printing 40, 50, 60 only. If I do 1 to 3, it will be printing me 40, 50, 60, 70, 80, 90. Cool. And now from these, I need to have, from each column, I need to have first to third. I'll be having 50, 60, 80, 90. So this is for the rows, this is for the columns. Make sense? And this is still basic indexing. If I want to have all the rows, 0 to 3, I don't need to specify anything, and it will be fine. Just like normal Python, but basic indexing for rows, for columns. All right. With the comma is the one which is basic indexing. If I were just to specify one only, that is basic indexing still, and it is second row index, 70, 80, 90. All right. This is submatrix. We have already done it. If I want to have the second column, all the rows and all the rows, print all the rows and the first column is, when I'm speaking it, listen to it. This is what it is doing exactly under the hood. All right. So 20, 50, 80. A vector. If I write the shape of it now, shape of it. Surprise, surprise. A vector, huh? Make sense? All right. Now we have done the basic indexing. Let's go to the, we have already seen the basic indexing. We did the basic indexing. We changed the slice value and it changes the A also. We have 999 right here in the matrix, nested matrix. In the A also, we have the same 999 because the slicing just created a slice, just created a view. It didn't create a deep copy. But if we do the fancy indexing, for example, I could have very well done print A fancy in this format, that on the A, we have 1, row index 1, 0, 1, 2, 4, 8, and 10. All right. If I print, what is the issue? A dot. Too many slices of an O. Okay. Okay, just a moment. All right. So I can have the A fancy like this also, in which it gives me, I want to do this. Okay, don't want to do this. I want to have the initial on. Okay, so 0, 1, 4, 5, 8, 9, 6, 16, 17, or whatever. 4, 6 is what is missing. All right, 0, 1, 4, 5. It's pretty similar to A dot slice that we have. Make sense? But now, if I change it to 0, 0 to 1, 2, 3, 4, 5, 6 and print A fancy, if I print it, then it will be 1, 2, 3, 4, 5, 6. But if I print A only, it will be giving me the earlier A on. It will not be changing it to 1, 2, 3, 4, 5, 6. So the learning from this is fancy indexing, not the basic indexing, which we did right here, which we did right here, which we did right here. These are basic indexing, but these are fancy indexing. In the fancy indexing, it ends up creating a deep copy. Never do fancy indexing, if possible. Always do the basic indexing. On all the tutorials on YouTube, they'll say that you can do this also, do this also, but they'll not distinguish that one creates a deep copy, one doesn't create a deep copy. And then you will keep on, my model is not running very fast. Make sense? Because I was not doing the basic indexing correctly. Make sense? I am using a lot of compute. Why? A lot of tokens. Why? Because I don't know how to do the basic indexing. Make sense? Now, the last task that we'll be doing today is Boolean masking, and then we'll stop. Firstly, we are creating a random number generator, RNG, random number generator, np.random. Anybody, any question till now? np.random dot default random number generator from 42. We will be seeing this a lot of times in our code. Let me decode it. Default random number generator is seeding from 42. It doesn't mean that the numbers start from 42. If I print random number generator dot standard normal, Rupesh, look at me. Why are you so sad? Standard normal of 1000. All right. Then print. Should I talk about more about dosa so that you are a little interested? You got married? Oh, that's why you're sorry.
Yeah, I did.
Sorry. All right. So we have a standard normal of 1000 elements. Cool. All right. We'll talk about the standard normals, but it is the seeding from 42 doesn't mean that the numbers are starting from 42. It doesn't mean that. What it means is 42 is just a code for an algorithm under the hood. If I provide it 100, it will be a separate algorithm. 100 is an algorithm of Lohit. And Moni made his own algorithm, which is 42 for random number generator. But what is the learning is not the seed. The learning from default random number generator, if you have specified a default, is that Moni's algorithm, who is 42, code 42, is going to generate the same random numbers. 100 is the code for Chianika. Chianika's model is going to make the same random numbers every time. Neither if you called it without a default seed, Lohit will end up creating different random numbers. If he runs it again, there will be different random numbers which will be created. And in testing, or when we are doing the matrix, when you are evaluating your model, it is very, very important. Because initially you created on your data something. Now that data has changed on. That's why seeding from a specific number is very important, and we'll be doing seeding from a specific number. Random number generator, if I print the type, if I want to draw an equivalent of random number generator, it is basically a generator only. NumPy.random.generator, which is just like an iterator. Iterator in Java or C++. It keeps on creating on the go. Next. Make sense? It's like an iterator. That is what it is doing. All right. And standard normal. Now let's come to the standard normal. What is the standard normal distributions? I hated my class 8 mathematics, but I have to learn it right now. What is normal distributions? Or sometimes called Gaussian also. All right. So if some machine learning engineer like Moni is throwing on some terminology at you, Gaussian, it basically means normal distribution. What is normal and standard normal? A normal distribution is basically a bell curve with mean as mu, can be anything. and sigma, that is standard deviation, is equal to sigma. And it is a standard normal distribution if the mean is 0, and standard for a standard normal distribution, the sigma or the standard deviation is 1. This is very important. It is called Gaussian distribution also. Within one standard deviation lies are 68% of the data. We'll be doing the confidence intervals, very important. And if you have to sound like a sophisticated machine learning engineer, then you have to say 68, 95, 99 rule. I am going to have 68, 95, 99 rule. Basically, what it means is within one standard deviation lies 68% of the data. Within two standard deviations lies 95% of the data. Within three standard deviations lies 99% of the data. And we will be using this for a lot of parameter tuning. Neither you'll see what Meet is a machine learning engineer. He just took the data. He just did it in the chat GPT. He just took the model from there. Akshay is his interviewer. He says, hey, can you do the parameter tuning? That why did you take alpha is equal to 0.1? Can't I do that? Naive machine learning engineer will be say, I'll take alpha is equal to 0.5. And I'll see if that result is better, if my accuracy is better. That is naive machine learning engineer. The sophisticated one says that 98% will be giving me that alpha 0.5 will be able to cover 98% or 99%. Based upon that, I will be taking the alpha is equal. My 0.1 is going to cover 99% of the. Why do I take 0.5? Why do I go over the data and overfit my data? This will be the talk of an experienced machine learning engineer. Naive one will say that I'll take alpha is equal to 0.5. All right. Experienced one will say that 0.1 is covering my 99%. Why should I overfit my data? By running my model again and again on the same data. All right. So all these things will be coming into the picture. Standard normal is mu is equal to 0. So if I print x dot mean over here, I didn't do a for loop. I just calculated the mean directly. Vectorized operation is pretty close to 0. Now the interviewer says, can you give me x mean? Okay, let's create the x mean, x dot mean. Give me all the numbers. You printed the x over here. Give me all the numbers which are going to give me, which are greater than the mean out of these numbers. For that, I will be creating something called a mask, a Boolean mask, which is basically x is greater than x mean. All right, I'll explain. And then mount on the x the mask. All right. And print x greater than mean, first 5 elements. Remember, they should be greater than this 0.-28 that we calculated, the mean that we calculated. All right. If I do this, if I run it, firstly, print x mean, that was correct. Am I printing x also? Let me not print x. All right, 0.028. And when we have done the masking and I have gotten the element which is greater than the mean, the very first 5 elements are these, which are greater than the mean. Remember, this is also greater than the mean. Huh? But under the hood, what it does is very revolutionary. If I print mask.shape, it will be giving me a shape of 1000 only. If I print the mask now, it will be giving me a Boolean array. It will be giving you a Boolean array of true and falses. So basically, On this array of 1000 elements, 1, 2, 3, I'm just taking an example. It's actually, they are standard normals. It does this, that my mean is 5. It does vectorized operations, that are you greater than 5, 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 are you? Not one by one, vectorized in parallel. And it gives a Boolean array, true, false, true, false, true, false. Every Boolean masking or Boolean indexing is going to do that. It is going to create a Boolean mask, an array of true and falses. And once you mount that Boolean mask onto the original array, it is going to just get all the true, false, true, false, true, false. It is going to compare with that. And it is going to give us the result like this. So if I do this, print x greater than me, which is the mask that we have mounted of that mask of Boolean true and falses, then it is just going to take those indices now. So now if I do this, x greater than me, then it is going to give us x greater than me. And if I take the shape is going to be 511. Out of those 1000, 500 elements were greater. It doesn't do a for loop that it is going to go one by one. It does two vectorized operations. One is this mask is created vectorized. I just need to specify x is greater than x mean. I didn't need to compare with the for loop. And a second vectorized operation, mounting the mask on the original array. Never in your this thing you should be doing any for loop based or dot apply or dot lambda based functions. Then you are going away from the vectorization, and then you will be thinking, oh, my model is slow. All right. Now x flipped is replace all the negative values with the 0. We already know in the mask what are the values which are greater, which are smaller. I don't need to do a for loop. All I need to do is x flipped is x, where x is a mask. Now I am not creating it separately. X is greater than, is lesser than x mean. That should be replaced with 0. All right. So I'm just writing the conditions on it. All right. I'm writing it incorrectly, I think. Just a moment. Okay. Yeah. X clipped is like this. X clipped, x is greater than, x is lesser than x mean, then make it 0. Okay, x dot copy. Make a copy first. And then it was sharing the same memory, that's why it was. All right. So x clipped is if it is lesser than 0, if it is negative, then make it 0. All right. And if I print the x clip now, there will not be any negatives. Print x, print x clip. I will not be having any negatives in this. All right. And this is the way that we can do the Boolean masking. I just need to create the Boolean mask, mount that mask on the x clip, which is the copy of the x, and make it 0. That's it. Not doing any for loop based this thing. All right. And in the checks, that way, what are we checking? X shape is equal to 1000. Mask is not empty. All right. So x, it was 511, remember? And greater than mean condition, we are checking that x greater than mean should be greater than x mean. Yes, everything is greater than x mean. And x clip should be greater than or equal to 0. That is what we are checking, that all the elements are greater than 0 over here. Why? If we have clipped them correctly, then that should be holding good. From tomorrow, we'll be starting with the broadcasting. We are done with some of the things that we had to learn about NumPy today. Anybody, any questions till now for NumPy? We'll be spending one more lecture on NumPy.
Yeah.
So regarding NumPy, I just had one doubt. I joined 15 minutes late. Will the recording be available due to time
Yes,
zone
yes.
differences?
No,
First 15
I will not. No, I won't give you recordings.
No. The logistical part, you were explaining something about the EDA,
Yeah.
so that be
No.
available.
The recordings will be available. Am I recording it? So sometimes I make a mistake.
Especially
I
the
don't record.
first 15 minutes, like, because it was the
No.
introduction.
I'll record. Yeah, it is recorded. Don't worry.
Perfect.
Lohit, go ahead.
Oh,
Go ahead, Lohit.
thank you, sir.
Yeah. I mean, when like you were performing, like I think Boolean masking. So you said like we perform vectorized operations. I'm just trying to visualize. Do we like have like a like how would I say a vector which is like just a true and false and like we have already taken a random list. So like
No.
and we are just sequencing.
That is a great question. What he is trying to ask over here. Okay, let me if you understood your question. That if I did this, right?
Right.
X mean is a one variable. All right. If I print X mean over here, it is one scalar. Huh? Let me talk in terms of machine learning. All right. X mean is one scalar, correct? Right,
Right.
Lohit?
Right. Yeah.
Where did I make a mistake now? Oh, not X mean.
Casing of X.
Yeah. All right. My life. It is X mean. It is one scalar. If I did it with the scalar, what happened under the hood? Huh? Is that what you are asking?
Yeah, I mean like it's the mathematical representation of vector, like we are multiplying.
Yeah. So if I have a vector like this, right? And just a scalar, how did it compare? What he is asking, did it create like this 5, 5, 5, 5, 5, like this? Is that what you're asking? That
Yes.
did it create for this scalar? It created a list and then it started. Remember 4 parallel operation for SMD only, for SMD part. Okay, just to make you realize that it will. Okay, 4 operations will happen, but for that 4, I need 4 5s also. Make sense? This is what Lohit is asking, right? That what happened under the hood? Actually, nothing. It remained a scalar on. And still we were able to pull off vectorized operation. How? It's something called broadcasting. Rupesh is an engineer who is at Bloomberg who gave us an idea that if you create a new list, then there will be a lot of space which will be required. In NumPy, I am going to do this, that I am going to imagine that it is a stretched data. I'm not stretching it. I'm imagining it broadcasted. Broadcasting like Delhi Doordarshan. It broadcasts from Delhi, goes to Ludhiana, my place. Make sense? So, Amritsar. So what happens? It broadcasts 5. Means it doesn't do any memory allocation. It just broadcasts 5. Broadcasts 5 like this. Make sense? So it is called broadcasting. Between a vector and a scalar, broadcasting happens like this, that it stretches the data up to these elements under the hood. Don't tell anybody. People don't know it. That's
So
the
the
concept of
max, yes. So the max
only a
stretch is
scalar.
based on
Only a scalar. Not an iota of extra memory. Make sense, Lohit? Are you in love with the machine learning?
yeah. It's interesting, yeah. Very interesting.
It is
And
broadcasted. So if I did
the
a scalar operation, if I did a Boolean this thing, it does vectorize the operation. But for the vectorized operation, I don't need an extra space. I don't. All these 4 operations happen just with 1 5. Always. That's it.
so the max stretch of 5 is based on the limit which is decided based on the SIMD, essentially, which is like 4.
It's not. Yeah, the maximum limit. How many operations it will be? That will be decided by SIMD.
Yeah.
All right.
Okay.
How many parallel operations? That is one part. SIMD is one part of vectorization. Remember, contiguous memory, caching, no interpreter. All those. Don't forget about. SIMD is easy to visualize. That's why I catch you over there. Doesn't mean the other things are not there. Let me tell you, in the vectorized operation, it is not the SIMD which is the most optimal. It is the C array, contiguous memory, no interpreter. That helps the most. All right. All right. Anybody else? That's a great question. We'll be doing broadcasting tomorrow. I'll stretch your imagination. In case of vectors, in case of scalars, in case of matrix and vectors, in case of matrix. You'll love it. Yes. Anything else? Bye, guys. Have fun. I'll post the video after 1 hour.
Jaspinder, sorry,
Yeah.
quick question. Is there a requirement to brush up any statistics from school, or you would
Yes. We will do it. We will do it in the class. But if you can, okay, if you want to be a great machine learning engineer, and you'll beat most of the people who are doing the MS and if you can read 8th, 9th, and 7th class mathematics, we will be doing it in our class. But if you can read about them and read a little bit about matrix multiplications, linear algebra, then you will find this class very smooth. Neither I will make it smooth. I'll try to make it smooth. But if you can read 7th, 8th, 9th class mathematics, then it will be really great. We will be going over it, but we'll be going some part of it. And you'll feel that I'm covering the same kind of things, but at an extensive level.
So can you just put down the topics that you think, if done as a prerequisite, could help us in the cohort?
Yep, I'll do that.
Awesome.
I'll do that. All right. In fact, in the curriculum also, it is mentioned linear algebra, probability, statistics.
Yeah, I was going through that, but it's like not a lot. It's not descriptive.
You won't. You're at. Okay, I'll ask you after recording. You will not need it.
Okay.
You will not need it. All right. It's just that, okay, for the first day, you are looking at something very new. All right, makes sense to us. All right. And you will feel overwhelmed a little bit, but you will be fine. All right.
Sounds good.
Just do the lab, you'll be fine. All right. You'll get used to it. It's just the first day that you are looking at the Shakespeare. All right. So you will get used to it and you will be fine. You don't need to, because I know that what's your level. All right.
Sounds good.
You can do it if you want to be a little bit more prepared for the thing, but you'll be fine. All right. Anybody else? Any other questions?